All right, let's dive in. As a propulsion architect, I spend my days living right where power meets control. And today, we are going deep on a piece of tech that is truly revolutionary, the digital brain of the P-13 eVTOL. Let's get started. You know, we've been promised flying cars for decades, right? It feels like they're always just around the corner. So let's start with the big question. Why aren't they filling our skies right now? Well, the answer might actually surprise you. The biggest roadblock wasn't about wings or fancy materials. It's not about the flying at all. It's about the thinking. We're talking about the incredible, mind-boggling complexity of the control system that's needed to make these things safe, reliable, and just plain efficient.
And that is exactly where the P-13 modular concept comes into the picture. What you're looking at is a totally radical design for a hybrid eVTOL. That's an electric vertical takeoff and landing vehicle. It's built from the ground up to solve the core problems holding this whole industry back. And the real key, the secret sauce, is the brain that connects its two modules, a combined vehicle control unit and flight control computer, or as we call it, the VCU/FCC.
Okay, so to really appreciate this solution, we have to start from the top. We need to define the exact problem it's designed to solve. Let's call it the urban mobility dilemma. So let's just break down what we're seeing here. On the left, that's pretty much the nightmare scenario for any standard eVTOL. You're running low on juice, you're over a dense city, and you've got nowhere to land and charge. But look at the right. That's the P-13's elegant solution. The flight module can actually dock with its own ground vehicle, which acts as a mobile charging station and a range extender. It's a total game changer. You see, the whole industry is basically hitting its head against two giant walls. The first is what we call the battery energy density bottleneck. Put simply, batteries just can't store enough energy yet to give us long, practical flights. The second wall, a massive lack of charging infrastructure. I mean, where are you going to plug all these things?
So how do you solve a problem that seems, well, unsolvable? You don't. You reframe it. And that brings us to the master plan behind the P-13. Its absolutely radical modular solution.
Here's where it gets really clever. Look at this breakdown. The designers separated the functions into two totally distinct, specialized modules. You've got the mothership, a long-range hybrid vehicle for the road, and then you have the flight module, a short-range, pure electric aircraft for the sky. By splitting these jobs, the P-13 just brilliantly sidesteps both the battery problem and the infrastructure problem in one go.
But as you can imagine, this really elegant architectural solution creates one heck of an engineering challenge. You have to build a single, unified brain that can master two completely different worlds, the fast-paced world of automotive and the hyper-precise world of aerospace. And each of those worlds has its own incredibly strict safety standards.
So how on earth did the engineers pull this off? Let's pop the hood and go inside the digital brain to really break down its layered architecture.
Okay, at the very top, you have the L1 strategy layer. This is the flight control computer, the FCC. Think of it as the pilot's co-pilot. It's handling the big picture stuff. Where are we going and how do we stay stable and safe? To guarantee that safety, it uses a triplex redundant architecture. That means you have three independent computers constantly checking each other's work. If one gives a different answer, the other two overrule it. It is the absolute gold standard in aviation. Right below that, you've got the L2 tactical layer. This is the vehicle control unit, or VCU. I like to call this the energy maestro. It's managing the complex dance of power from the engine and the batteries, making decisions millisecond by millisecond. For reliability, it uses a dual duplex architecture. That's basically one system doing all the work with an identical twin on hot standby, ready to take over instantly if anything goes wrong. And this diagram shows how it all fits together. You can see that perfect hierarchy we just talked about. Strategy, the FCC at the top. Tactics, the VCU in the middle. And execution, the motor controllers at the bottom. Now, this strict separation is absolutely critical. It creates what we call fault isolation. That means a problem in one layer, say a motor fails, can't cascade up and crash the whole system. Every part has its job and only its job. It's the very core of a safe, robust design.
So now that we get the architecture, let's see what it can actually do. It's time to watch this seamless power dance that the VCU performs.
The real genius of the VCU can be seen in three, let's call them signature moves, that show off its incredible speed and precision. Torque fill, K0 synchronization, and active vibration damping. First up, torque fill.
You know that tiny delay you feel when you step on the gas in a regular car? That turbo lag? Well, the VCU sees that coming from the engine, and in less than 10 milliseconds, that's faster than you can blink, it tells the electric motor to instantly fill that power gap. The result? The pilot just feels one smooth, perfectly linear push of power. It's seamless.
Next is K0 synchronization. Now this is tricky. This is when the engine needs to connect to the propellers while you're already in the air. If you get this wrong, you'd create a huge, jarring shock wave through the whole aircraft. So to prevent that, the VCU has to match the speeds of the two spinning shafts to within just 10 RPM. That is surgical precision. And it does it so perfectly that the transition is completely unnoticeable. Performance is cool, but in my world, in aviation, safety is absolutely everything. So let's look at the foundation of trust for this entire system, its fortress of redundancy. The whole design philosophy starts and ends with this single, non-negotiable requirement. The probability of a catastrophic failure must be less than 1 in a billion per flight hour. Let that sink in. That is the exact same standard that every commercial airliner you've ever flown on is held to. It's the bedrock of building the public trust we need to make this industry fly. So how do you hit a number that incredible? You do it with the strategy called defense in depth, which is all laid out here. It rests on 4 main pillars. First, propulsion redundancy. It can lose a motor and still fly fine. Second, control redundancy. That's the primary and backup systems we talked about. Third, energy redundancy, using separate partitioned batteries. And finally, communication redundancy, with multiple data paths. The main takeaway here is simple. There is no single point of failure in this entire design. Now this is what makes this VCU/FSE so unique. It has to meet the absolute highest safety standards from 2 different worlds at the same time. On the automotive side, that's the top ASIL D standard. And on the aerospace side, it has to meet the level A standards for both software and hardware, which is the most stringent level you can possibly have. Fusing these 2 incredibly demanding philosophies is what makes this system so unbelievably robust. But look, a blueprint is just a promise, right? And that promise has to be proven. So let's look at the absolute gauntlet of testing the VCU/FCC has to survive to earn its wings. Verification follows this really rigorous process called the V model, which moves step by step from pure software all the way to physical reality. You start with processor in the loop, just testing the code on the actual computer chip. Then you move to hardware in the loop, where you connect the real controller to a full flight simulator. Next up is the Copper Bird, a test rig for all the wiring to check for any interference. And finally, you get to the Iron Bird, a full-scale ground replica with all the heavy metal of the powertrain, making sure it all works together before it ever leaves the ground. In the end, success isn't just a feeling, it's a set of hard, quantifiable numbers. These are the key targets it has to hit. Real-time performance has to be under 10 milliseconds. System availability, under 5 seconds. If a fault happens, it has to recover in less than 20 milliseconds. And software integrity demands 100% code coverage. There's no gray area. Meeting these numbers is what earns you the right to fly. So when you look at all of this, the elegant architecture, the layered safety, the exhaustive verification, it all leads to one conclusion. From an engineering standpoint, the digital brain is ready. It's here. The only real question left is the world ready for the flying car?